Hi everyone, we are back and we are going to do some chemical diffusion and kinetics problems too. So we see here that Fick's first law here has very similar solution or shape essentially, or basically functional form as our Fourier's law. And then also our Fick's second law given here, as long as our diffusivity is not dependent on concentration, has a very similar form as our heat transfer equation. So again, we can solve for 1D steady state diffusion just like we did previously. We'll have two constants and we see a linear function that emerges if we're just looking at some certain length L. We can solve for, again, transient solutions too, time varying. We can set, again, boundary conditions, initial conditions. We can solve that function. Excuse me. And we can solve it, as you can see here. We'll give it a little bit of time. Again, solving our equation, boundary condition, initial condition is a function of x and t. And when we get that solution, we'll essentially obtain this here. And actually, I will skip. Actually, let's let it run for a little bit. And we'll see several different types of examples. But we'll do this one quite quickly. Obviously, they can get much more complex. And as you will see in your in-class activity in your problem set too. Let's take the first 100 terms. You don't need to look at that. Actually, we do need it to. Actually, and we can solve plot. We can do a prop solution for basically C actually, as a function of x and t, and then we can do slash dot d goes to diff, and then we can do manipulate our diffusivity here. Hope this works. Unfortunately, it did not. So what we can do is look at a solution. So one of the things we may have to do is go x2, x1, slash dot here. We need to bring out essentially these variables. X goes to x1, t goes to t1, and then we can settle this up right here. And t goes to t1, comma, d goes there, t1, and now we've got our solution. So now we can look at our problem, and then what do you know, as we go forward, actually even as we increase that diffusivity, initial condition was what? Where time t equals 0, everything else is 0. Over time, we don't have a no flux boundary condition, so you see that this is different from our other heat transfer, the insulated boundary condition. If we were insulated boundary conditions, so for example, if we instead said that basically the derivative of C with respect to T, actually we need to look at C with respect to, actually we can look at back at, actually just copy these ones here. No need to reinvent the wheel effectively. So we can look at our no flux boundary conditions, which I believe we had here. We'll just copy these over here. Way down, we don't need to go here just quite yet. So, for example, take, so 10, except C, come here, derivative of 1, 10. If we do no flux boundary conditions now, we solve this as long as d is greater than actually you can solve this. Actually, that's quite a easy solution. Again, zero flux boundary conditions, they can't get out, so simple solution. Excellent. Next time we'll look at a couple of vibrations types of examples, and we'll move forward then. See you in the next video. Thanks. Bye.